Okay, so we're hitting some uncharted territory for many of you when we get into logarithms. And in this section, 5.1a, we start getting into exponential functions. And just remember that a linear function has a constant rate of change. Okay, so the outputs change by the same amount for each unit. Okay, so as we add to our x, our y goes up the same amount here as it did here. Okay, what happens with an exponential function is it's multiplied. So as our x goes, our y may go this far the first time, and as our x goes that far again, it may go up a lot more because it's multiplied rather than added. So then we get a graph that kind of looks like that. If you ever heard the phrase increases exponentially, that means that it increases really, really fast, because notice how as our x gets bigger, our y just kind of plods along and grows. But here, as our x get bigger, our y increases really fast. So that's kind of gives you an idea of what we're looking at with exponential functions. So pretty much what we're looking at is a function that looks like this. Okay, where b is a number, and it's called the base, and it has to be a number that's greater than 1. Okay, so what we've got here is a variable right here in the exponent position, and that's what we're trying to figure out, is our x here, so that we can take the base to that power and get our y value, or our f of x value. Okay, so they give us a whole bunch of stuff. Bottom of page 315, they give us the graph of exponential functions and all they look like. Top of page 316, which is really some good stuff to write down, because it tells you how these exponential functions are transformed based on what they look like and compared to this general form of the exponential function. So, for example, the first one says we shift vertically if we add a k to that, and we shift it up if k is positive, we shift it down as k is negative. So if you follow down that little table there, it tells you what to do there. So then in example 2, and then example 2, we will base it on that table that I just referred you to, and it gives us a y equals 3 to the x power. And they're saying, okay, so for a, sorry about the plane overhead, I'm outside watching my dog catch flies and trying to get some lecturing done while it's nice and warm and in the 70s outside here in Soldotna, Alaska. Okay, so this is a. And they're saying, okay, so what is going to happen to this function compared to this one? Well, if we look up into the table, it says that if our exponent, if we subtract a number from it, right there, it is going to shift it 4 units to the right. So whatever our graph looks like, it's going to shift it 4 units to the right. Okay, that's pretty much all it's going to do there. Okay, so if we go to B, B gives us y equals 2 plus 3 to the x minus 4. Okay, so we change from just the y equals 3x to putting a 2 there and putting a minus 4. All right, so we already said that the minus 4 moves it 4 units to the right. But what does this 2 do to it? This 2 tells us that we go up 2 units. Okay? So that's what we've got. We've got 4 units to the right, and this 2 here means that we go up 2 units. All right, so it's a little bit different. The book says that on a vertical shift, if you look at the very first one, they give us g of x equals b of x plus k. And if this is a plus sign, it means that it shifts it up k units. Well, all we did is put that in the front. We could put it afterwards here so that it looks more like that, but just be aware that they didn't do that. They put the 2 at the beginning. Doesn't really matter. Alright, so C says that if we have y equals 5 times 3 of x. So the only thing different between our first one right here and this one is we multiplied by 5. And if you look at multiplying by a 5, what are we going to do? We are going to stretch the graph by a factor equal to this much. And if we look at the table in the middle of page 316, when we multiply a number here by this, it's going to stretch it or it's going to compress it. But when this number is bigger than 1, it's going to stretch it vertically. If this number is smaller than 1, it's going to compress it vertically. Okay, so this is the vertical. The horizontal stretch is if there was a number multiplied by this x here, and there's not. Okay, so it's not going to stretch horizontally. It's going to stretch vertically because there's a number multiplied by the entire parenthesis here. This is not an exponent, whereas when it's multiplied by an exponent up here, it will horizontally stretch or compress it. All right, so I'm going to skip over example 3 and continue going on through here. I don't want to spend, a ton of time with all of the details with this. Whoop, there we go. But because sometimes when they get into these exponential functions, it gets to the point where it overdoes it, okay, with way too much complicated stuff. So I'm trying to give you everything you need, but not confuse you at the same time. So let's see if we can follow that. All right, so if you look at example 4, talking about inflation, they give us a formula here right above example 4 that is S equals P times 1 plus R to the T power. And that T power is time. P has to do with the amount of money you invested. R is the interest rate, and S is the future value of that investment. So how much money are you going to get when you invest that money? So A says, looking at that information, for example 4, write the function that gives the cost of a $10,000 item T years after 2012. So what we're doing is we're just putting numbers in there that they give us. So they gave us 10,000 for P, and then we've got 1 plus, what was the interest rate there? 0.04, and that's at T power. Okay, and then we just add those. We get 1.04 to the T power, and that equals what we're looking for. Okay, so let's jump to part C, since part B is a graph, and you can look at that and see how they did that. Let's look at C. If an item costs $10,000, okay, that's our P. In 2012, use the model to predict its cost in 2025. So, as years go by, the price of things goes up. So 2025 is 13 years past 2012. So 13 is going to be the number we use for T. So Y equals our 10,000 that it costs now, and then we're going to put 1.04 to the 13th power. Okay? And that is going to tell us that in 13 years, that item will now cost this much once we have inflation. And so that's pretty much what we've got there for example 4. Example number 5 is pretty much the exact same, so we're going to jump past that. I do want to go into exponential decay models, which is on page 320, and we'll start that on a new video because there's not a whole lot left of this section. So we'll finish up with 5.1b.